Welcome to this proof of the chain rule. Today, we won't just memorize the formula, we will visually understand why the derivative of a composite function is the product of its derivatives. To analyze the derivative of the composite function, h of x equals f of g of x, we start from the formal definition of a limit. We want to study how the entire system responds when the original input, a, undergoes a very small change h. Let's visualize this process. In the first set, we have input and its increment. By applying the function g, these transform into g of a and g of a plus h. We will call the difference between these two intermediate values k. Thus, we define k as the intermediate increment generated by the inner function g. Finally, the outer function f takes these intermediate values and projects them into the last set. The final change we want to study is the rate between this output change and the original h. Here comes the classic algebraic trick. We multiply and divide the expression by k. This is equivalent to multiplying by 1, so the equation remains identical as long as you assume this increment k is not 0. If the inner function g is continuous, as h approaches 0, the intermediate change k also shrinks to 0. This allows us to split the limit into two independent parts, the derivative of the outer function f and the derivative of the inner function g. Multiplying both limits, we obtain the famous chain rule. The derivative of a composite function is the derivative of the outer function multiplied by the derivative of the inner function. But watch out. This intuitive proof hides a mathematical flaw. What happens if the increment k becomes exactly 0? Imagine that the inner function g is constant over a small region. In that case, the increment k is exactly 0 for many values of h. By trying to divide by k, we would be performing an undefined division by 0. The previous proof ceases to be formally valid. To solve this problem rigorously, we resort to the definition of differentiability using little o notation. This allows us to express the increment of function f as its linear part plus an error term that vanishes much faster than k. Now, we substitute y with g of a. We obtain the exact difference of the composite function without needing any forbidden division. To find the derivative, we divide the entire equation by the increment h. Notice that here we are dividing only by h, which we know is never 0. Finally, we analyze what happens to the error term. Rewriting it by multiplying and dividing by k, we see that the first term approaches 0 by definition of little o, and the second approaches the derivative of g. Therefore, the entire remainder vanishes upon applying the limit. The remaining term vanishes, and we arrive at the exact same result, but this time with absolute mathematical rigor and regardless of whether k becomes 0. The chain rule is one of the most powerful tools in differential calculus, and now you understand both its visual logic and its formal rigor. See you next time.